Okay, so this is what we're going to do today. We have this exercise. You have different numbers depending on your ID. So I'm going to do it with 40 and 30 feet. And we have this opening, and this opening is half. Okay, so that would be 15 by, no, 10, because this distance is 10 by 15. Because according to my numbers, this is 30 and this is 10. Okay. And this is 15. So now the first question is, if we have three different beams, we have B2, B1, and B3. So the first, what beam is bearing the maximum load? 1, 2, or 3? 2. 2. I agree with that. Okay, and why is that? Okay, so if I divide this into different sections, okay, and now this thing here. So, okay, so all this area is going to the B1. The same area is going to B2, but this part is going to B2, and this is going to be 3. Okay, so if we have this, all this area belongs to B3, this area belongs to B2, that belongs to B1, and that belongs to B2. Okay, so B2 is bearing more weight than B3. It's bearing just this tiny area here. This is an opening. B1, it's bearing this half. And B2 is bearing this half plus this half. Okay, so B2, if we have to calculate only one beam, it would be B2. Okay, so what's the length of B2 is 30. And now we need to calculate the load on that beam. And here we have a live load and dead load is 80 plus 20. So the total load is 100 square feet. And then we have the weight of the beams. It's 50 pounds per foot. Okay, so let's put everything here. So the beam is 20 pounds per foot. And the slab is 100 pounds per square foot. By the way, this is pound per square foot. Okay, so we have 100 pounds per square foot here, and we have 100 pounds per square foot there. Okay, so I'm going to have the beam. The length of that beam is 30. Okay, so that's the length of the beam. And we're going to have columns. So what is a column? A column is a reaction. So we have a reaction here, and then we have another reaction there. So that's the geometry of the beam. The span is 30 feet from this point to that point. And now I have to consider the weight. Okay, so, and we're going to split this into three different arrows to be. Okay, so I'm going to have, I'm going to break it down into three different parts, meaning three different loads. So the first one is 50 pounds per square foot. Okay, so the weight of the beam. So this is a uniformly distributed load, and it's 50 pounds per square foot. Sorry, not per square foot. This is 50 pounds per foot, not squared. So this is the uniformly distributed load. And then what is the uniformly distributed load of this half?
50.
Sorry?
50 pounds per foot squared.
50. Why?
Since that'd be half the actual slab.
Yeah, it's half, but the weight of that slab is 100 pounds per square foot. So it's not about, and then I have the half, I have half the slab, but I have to turn pound per square foot into pounds per foot. So I have to multiply by something. But
Is it 45,000?
45,000
No, pounds per foot.
pounds per
You
foot.
gotta multiply by
You have to multiply by
the width.
the width. And what's the width?
30.
30?
15.
Three people here, well, four people in four different options. So it's, so what's your opinion? By 15. Okay, so who said 15? You said 15. So you are, okay, great. I think you are both right. Yeah, it's 15. Okay, so if we are looking at this from this direction, I have to multiply by the length or the dimension that I don't see, because I see this dimension. This is 30, so this is 30. So this part of the beam is 100, or this weight is 100 pounds per square foot times the dimension that I don't see. So what dimension is that? It's half that slab, so it's half 30. So that would be 15. Okay, so this is 1,500 pounds per foot. So this is that uniformly distributed load. Okay, so this is way bigger than this one. So this is 50 pounds per foot. And I'm going to type pounds like this. And this is 1,500. So we have more weight coming from that slab. And now, what about this? What is this load? This half of the slab that I have here. 5.
500. Yeah, that's what I meant.
Sorry?
So 500 pounds per foot.
It's 500 pounds per square foot.
Yeah.
So it's 100 times 5. Why 5? Because it's half 10, so this is 5. But This is a uniformly distributed load, but it's not uniformly distributed throughout the beam. Where does it stop? It stops here, because here we have the opening. Okay, so we only, if we look at this, on the left, we don't have anything, and on the right, we have this, the uniformly distributed load, which is 100 times 5, so this is 500 pounds per foot. Okay, so if you look at this, I think everything makes sense. So we have the beam weight. So this is a uniformly distributed load, the whole length. Then we have that slab. That slab goes from this point to that point. So it's the whole length, 30 feet. And the uniformly distributed load is 100 times 15, because it's half this dimension. Okay. And this uniformly distributed load only affects, if we look at this from this point, it affects the right part, the right half of that beam, and it's 100 times 5. Total 500 pounds per foot. Okay, so this is the first thing that we have to understand. We can break it down into different parts, and then we can solve different parts. We can do everything together, but I think this is clearer if you divide the problem into 3 small problems. I think it's easier to tackle. But we can do the same thing, working with the total load. We can add this up and then solve the beam with the total load there. But let's do this. So we are going to solve first this first option. Okay, so this is 30, the length, 50 pounds per square foot. What do we have to do? First, we are dealing with beam 2, so that's why this is always beam 2. Okay, so because this is the beam that it's bearing the maximum load. And then the shear diagram of the beam. So we're going to do this 3 times. Okay, so we're going to copy this. B here, and finally this one. So we're going to do these 3 different problems. Very easy. And then on Tuesday, we will do the same again, but considering the whole load. The result should be the same, but probably the procedure will be slightly different. Okay, so what is, if we have this, what is the first thing that we have to calculate? We have to calculate reactions. So what is this reaction? What is the value of this arrow?
$750.
Hmm?
$750.
750. Any other opinion? I don't trust him.
It's not 50 times 30.
Yes. So it's a uniformly distributed load, 50 times the length, 30, and we have 2 reactions. If it's symmetrical, it's just divided by 2. Okay, so that would be 750. So that reaction is 750, and this reaction here is 750. Okay, what about this one?
$1,500
Times
30
divided by 2. Okay, so that would be it's the uniformly distributed load, 1500. Fifteen hundred times 30, the length, divided by 2, because we have two reactions. So this would be 22,500. 22 and 500. And it's symmetrical. So that will be 22,500. So now this one is slightly more complicated because we cannot divide it by 2. So what shall we do here? First, here we need the resultant. Okay, so there will be a resultant of this uniformly distributed load. It will be here in the middle of this one. And that resultant is 500 times the distance. And the distance is 15. I'm going to so that distance would be 15 feet. Like this. Okay, so this distance is 15 feet, and the load is 500 times 15. And this is 500 times 15, 75 tons. Okay, so now we have turned this uniformly distributed load into this individual load applied in the middle of the uniformly distributed load. So it's 7.5 . Okay, so that distance is 7.5 . Away from this point. Here. Okay, so I think now it's clear. So this resultant, it's applied here, dividing this uniformly distributed load by half. So the total length is 15, so that would be 7.5. Okay, so I think with this, I can have equations. So we have reaction 1 and reaction 2. R2, if this is the second one, it's going to be slightly high. Well, it's going to be higher than this one because the load is closer to this one. Okay, so that makes sense. The closer the load, the bigger the reaction, and the farther the load, the smaller the reaction. And we have to apply moments. Okay, so we have to take moments. We can take moments at this point. So if we call this R1. Then we call this one R2. Okay, so the basic moment equation at this point. So what's the moment of R1? R times 30. Because the length, the distance between this force and this point, it's 30. And is this clockwise or counterclockwise? Okay, so this is moving. So this one is moving this clockwise. Okay, so R1, it's moving the beam around this point clockwise. The resultant is moving the this counterclockwise. Okay. So there's another force moving this counterclockwise in this direction. And what is that value? That value is 7,500 times the distance. Now the distance is not 30, the distance is 7.5. Okay, so if we have this equilibrium, that means that this has to equals, so this equals that. So now we can calculate R1. So R1 would be 7,500 times 7.5 divided by 30. So this is 7,500 times 7.5 divided by 30. And this is 1870. And what about R2? R2 is the vertical load, 7,500 minus 1875. This is R2. This is 7,500 minus 1875. 5625. So that equals 5625. Okay, it makes sense. This is greater than this one because it's closer to the load itself. So this reaction is more significant than this reaction because it's closer to the load.
I think just in the middle one, you forgot to divide it.
I forgot to divide it by 2.
Yeah, the middle one.
This one?
Yeah.
Let me check. 1,500 times 30. No, I divided it by 2.
Oh, I did. So 1,500 times 30.
It's 45,000 divided by 2, 22,500. Okay, so now we have broken the problem down into 3 different small problems. And the first is I have to calculate the reactions, okay? Then the next step would be to calculate the shear diagram. And finally, I will calculate the bending moment. And then we have to add everything up to see what we get. Okay, but when it comes to the shear diagram, I think it's quite simple because we just we have the beam here. So the first thing is this arrow, this is 7,500. No, 7,500, no, 750, sorry. 750 going up. Here we have another 750 going up at the end of the beam. And then the shear diagram is just a line connecting this and this. So that's the shear diagram of a uniformly distributed load in a symmetrical beam. Okay, so this is quite simple. This one, it's gonna be the same with different numbers. Okay, so the now this arrow is not 750, is 22,500. And this arrow is the same. Okay, so that's the shear diagram of that beam. And this is different. Okay, so let's do this one. What do we have here? First, we have an arrow going up. So this is 1,875. So it's bigger than the first one, smaller than the second one, so something like that. And until we have this, there's nothing. So if there's nothing, the shear diagram is horizontal. Okay, so at this point, we have an arrow going up, then we don't have anything else going horizontally. And finally, we have another force going up. That force is 5,625. So from this point to that point, we have to go down, and finally we go up. So this is the shear diagram of that beam. Okay, because we have broken the beam down into 3 different beams, but now we have to give the total value. So my question is, what is shear diagram of the beam? Okay. What is the maximum shear stress or shear value? What's the maximum shear of that beam?
The 125,
Sorry, 28 point
28,125,
what?
22,500 plus 5625
Yes, and what about the 750?
plus 750,
Yes.
28,875.
Yeah, that makes sense. But okay, so what is I mean, this is 750 and this is 750. Okay, this is 22,500, this is 22,500. This is 180, yeah, 1,800, and this is 5,600. So the maximum value is gonna be at this point. So I have to add up this one plus that one plus that one. Okay, so the maximum shear value is 750 plus 22,500 plus 5,625. Okay, so that's the maximum shear value. How much was it, Zach?
35,000,
35,000? What?
100.
One. Units?
Oh, wait, no, it's not, that's mine, sorry, I forget.
I do it.
Yeah,
Okay.
sorry.
Let me do it. 24, 500, 500 plus 5,625 plus 750. It's 28,875. Pounds. Okay. Good. So this is how it works. We have three different, and we have to calculate the point at which the shear value is the greatest. So obviously it's not going to be here because the shear value here is 0, the shear value here is 0, and the shear value at the middle of this point is 1,875. So this is not the most interesting point. The most interesting point is in which the shear value is the greatest. So yeah, so it's this the right side of this beam. Okay, what's next? The bending moments. So we can do this, and we're going to calculate the bending. What's the bending moment of a uniformly distributed load?
W times L squared by 8.
Okay. So this is W times L squared divided by 8. So I'm going to bond and yeah, so that's it. And this will be true here and here. It won't be true here because this is not a uniformly distributed load throughout the beam. Okay, so that would be something different. But let's say that here in these two cases, and where was this one? Okay, so if the uniformly distributed load is, so it would be something like that. Okay, so that would be the maximum bending moment here because we have a very low load. If the load is greater, so this bending moment would be more significant. Okay, so how much is this? What is W? It's 50. Times L square is 30. It's 30 divided by 8. So how much is this? This is 50, the load, times 30 times 30. This is L square divided by 8. Here units are important. It's 5,625. 5,625 pounds. Good. Okay, so those are the units of the bending moment. What about this one? So this one, the load is 1500. So this is 1500. The length is the same, it's 30 square divided by 8. So this is 1500 times 30 divided by 8. We got 168,000 750 pounds per foot. Okay. So let's put this in kilopounds per inch, because that's the unit that we are going to use. It's kilopound kilopound times inch. Okay, so in kilopounds per inch, that would be 5.625 times 12. So this is 67.5 kilopounds per inch. And that one is 168.750 times 12. So this is 2025 kilopounds per inch. Okay, so you shouldn't have any trouble calculating these two bending moments, because for a uniformly distributed load in a symmetrical beam, it's always this value. So now we have to calculate this. Okay. So let's do it. So let's open a new slide for that bending moment. Because I think it's worth it. Okay. I don't know. Well, I don't know. Where will the maximum bending moment be in this beam? Is it in the middle of the beam or here? I guess. But we can find out, okay? So I'm going to do it at different points so that we understand what we are doing here. So we have to copy this. And I'm going to cut this beam right here. Okay, at 15 feet. So the beam length is 30. So I'm cutting that beam here before we notice the uniformly distributed load. So what do we have here? We have just the reaction, because we don't have any load in this half of the beam. So we have the reaction. And if the reaction is moving that beam in this direction, okay, so there should be an internal moment here. So this reaction, this arrow, it's moving the beam in this direction. But there's something inside the material that has to be the opposite rotating direction. Okay, so if this arrow is moving this here, inside the material, it should be that way. So if the bending moment is that way, that means that we have tension here. And we have compression there. Okay, so this is what bending is. Bending is a combination between tension and compression applied at different points of the material. Okay, so at the bottom we have tension, at the top of the beam we have compression. So this is what we have here. Okay, and how much is this that moment? It's quite easy because the moment itself, if we want to calculate the moment, equals the force 1875 times the distance, and the distance is 15 feet times 15. Okay, so that value is 1875 times 15. It's 28, 125. Units, pound per foot, or pound times foot, sorry. So that's the bending moment there. Okay. So now, let's keep going. And now I'm going to calculate the bending moment, but not at 15 feet from the first reaction. I'm going to calculate this at this point. Okay, so this point is 15 plus 7.5. So this distance now is 15 plus 7.5 is 22.5. 22.5 feet. Not 2.2. 22.5. Okay, so in 22.5, what the hell do I have here? I have a uniformly distributed load. Okay, but only half this uniformly distributed load. So okay, so now the distributed load is just 7.5. And we do have a resultant, but that resultant is not 500 times 15. The resultant here is 500 times 7.5. So that resultant is 500 times 7.5. It's 3,750. 3,750. And what is the distance? It's not 7.5, it's half 7.5. So that distance is, what is half 7.5? Divided by 2 is 3.75. Okay, so when we are breaking the, or we are dividing the beam, because I want to calculate the moments at the point in which I think it will be the greatest value. So it's in the middle of this uniformly distributed load. Okay, so this uniformly distributed load, it's 7.5 here, and then the resultant is in the middle of this 7.5, so it's 3.75 away from that point. Okay. Okay, so now we have the effect of two different things at this section. So we have R1 moving this clockwise, so the reaction should be counterclockwise. So that moment is 1875 times, now the distance is 22.5, it's not 15, it's 22.5, and nothing else. So this is 1875 times 22.5. It's 42,170. 1,175. 187, 171, 87.5 pounds per foot. Okay, but now I have the effect of this force. So this force is moving this counterclockwise. So I have another moment, that's the reaction. Okay, so if this force is moving this counterclockwise, the reaction inside the material should be the opposite direction. So what is that moment? That moment is the force, it's 3750, that's the force, times the distance, and the distance is 3.75. So 3750 times 3.75. So this is 14,062. There you go. So there are two different moments. It's both moments, they are trying to rotate the beam in different directions. So the resultant is now I have to subtract one from the other one. So let's make it positive. So I'm going to subtract 42,000 minus 14,000. Okay, because I assume that it's going to be positive. But what you have to understand is that the effect of the forces is different. So I can't add up these two moments. I have to subtract this one from that one, the other way around. But this is what I'm going to do now. So if this is the first one, minus 14,062.5 equals, so this is 2. Okay, so this is 28,125. 125. Units, pound, times foot. That's the bending moment here. Which, look at this, and look at this. Does it make sense? I mean, if something like that happens, it might be like, there's an epiphany, or okay, so why the hell we have the same number? Or most likely I have made something wrong. Okay, so sometimes that when I this is when I find something like this, like, oh, who could think that this is going to happen? I tend to think that I have made a mistake. So I'm going to double check. Okay, so I'm going to double check. So I'm going to do this from a different direction. So I can cut this beam. And I'm going to do that from the right instead of starting on the left. I'm going to start on the right. Okay, so here I have only this tiny portion of this beam. This is 7.5. This arrow is gonna be 5. So that's the reaction. 5625. And this resultant is 7500. Okay, the reaction is 7500. And now I want to calculate the moment here. What is the distance? This distance is 7.5. Okay, so the length of this red bar is 7.5. And the distance between this resultant and this point is 3.75. So I'm going to do it quickly. So I'm going to do this 5625 times 7.5 minus 7,500 times 3.75. And let's see what I get. So this is 5625 times 7.5 minus 7,500 times 3.75. I do this. And now I get, what the hell? Let me do it again. 5625 times 7.5. 32. Okay. Minus 7,500 times 3.75. And the result is 14.
Why didn't you just,
What?
you just said 28, 125 for a second, then what did you put?
I don't get your. So the problem is this 7,500. I copied this 7,500 from this arrow, this resultant, but it's the whole uniformly distributed load. But now I have only half. So it's 3,750, you know, because it's 500 times 7.5. Yeah, so that was the mistake. This is not 7,500. This is 3,750. So now this is not 7,500. This is 3,750 times this, and now it's going to work because it's 5, 6, 7.25 times 7.5 minus 3,750 times 3.75. And this is 28.1.
I can't see where I went wrong.
So okay, so we are calculating the column now. We have calculated the beam with the section modulus. It's the maximum bending moment divided by the stress. So the maximum bending moment, let me check if I did it correctly, because the maximum bending moment is this. It's 2,430 kilopounds per inch. Okay, so that's the maximum bending moment. The stress in steel is always 30 kilopounds per square inches. So we have 81. We go to the catalog, and we need the section modulus that it's greater than 81. So this is the correct answer. Yes, I double checked, and this is it. Now for the column, we have the maximum shear stress, and this is the maximum shear. Okay, so we have to apply this vertical, it's compression, because columns are always working on compression. And we have the length of the column, 30 feet. It's quite long or quite tall. So I think we have to use the buckling formula first. So another question is, what is the buckling formula? Okay, so that's the buckling critical load. Okay, so I have to invert this because now I want to calculate the moment of inertia based on this load. Okay, so that's my load. So this is F. And now I have to calculate I. So what is I? So if this is the load, that equals E. What was the Young modulus?
Young modulus.
Said 30,000.
30,000?
No, I'm just, I never look back to what the skills like.
Okay, let's do it again. I always remember the megapascal.
Yeah, it's 30,000.
It's 30,000.
30,000 kilopounds per inch squared.
It's 30,000 kilopounds per square inch. Times I, this is what I have to calculate, times pi 3.14 square. And now I have to divide this by L square. So what did we do? We turned everything into inches, and then we.
Yeah, make it easy.
Okay, so it's 30 feet times 12 inches square. Okay. And now we have to calculate this number. We have to calculate I. So let's do it. If this is the value and we have a catalog, again, if this value is way bigger or smaller than the values that I get from the catalog, I should double check. But if, okay, so we have this catalog here now. Okay, this one. And we have the moment of inertia, it's 12. Wow. So it's 12,000.
Mine's 16,000.
Yours is 16,000.
CO2.
Yeah, so you know what? Because nobody's crazy enough to make a 30-foot column with such a big weight. Okay, so that's why it's not.
COC.
Okay. But look at this. Look at this. If we go to the other catalog, if we go to the American Beam Standards, here we have values that are even smaller than those, okay? Why is that? Because with columns, we have to move most of the area away from the center point. So look at this. Can we use this? This works perfect for beams, but it doesn't work at all for columns. Okay. So if you look at steel columns, look at this, okay? So we have either these kind of elements. It's not an I-beam. This is
Why?
yeah. So we can have square elements, we can have round elements, or we can have this. This is the typical Mies van der Rohe column. Okay, so the Barcelona pavilion, he's always using this kind of thing. So he's moving most of the weight away from the center point. Okay, so that makes sense in terms of the shape of the column. Okay, but that shape doesn't work at all. Okay, so this American standard doesn't work at all. So if we have steel columns, most of the area should be away from this. And we can be creative. Okay, so most of the area is far from the center point of the beam, because that prevents buckling from happening. Okay, so that's why we are using either hollow elements or elements like this for columns. So anyway, we don't have a 30-foot, or if we have a 30-foot, it can be like, so we need very thick elements. So I don't recommend you do that, okay? So because 30 feet, it's like 2 floors. So if we have a slab here, we can break it down into 2 different columns, and then it will be only 15 feet. Okay, so imagine that this is 15. If this is 15 feet, because we have 2 floors and we break down the column into 2 different parts, 15 and 15. Now this number would be yes, I have to divide this because it's 30 times 12 square. So that would be 15 divided. 30 by 12 is 360. Times 15. That number will be 3,203. Okay. So if we divide this in, if it's not 30, it's 15. That number will be around 3,200. And if this is around 3,200, yeah, we can select one of those beams here. Okay, so sometimes, why do we need such a tall column? If we don't need it, and if we can break it down into 2 different parts, it's more efficient in terms of if I don't have any other option, it has to be 30-foot tall, then it will be penalized because of the buckling, and then I will have to do this. Anyway, so those are design decisions. You can calculate as a continuous beam, or you can say, what if I break it in the middle and I make 2 different columns, shorter columns? Probably this is the wisest decision. And when it comes to the structure, aesthetics is not that important. It's first, it has to bear all the loads. Safety is important. But second, economy. If it's something more economic, something cheaper, why not? Okay. So that's it. With 30, we don't have, if it's 30, depending on the numbers, but probably we won't have a value, and this is 32 by 32 inches. Okay, so 32 by 32 inches. Look at this. It's a square, 32 by 32. So it's too big. It doesn't make sense. If we divide this into two different columns, then we can select this. Well, it's 24 by 24, so it's a lot, but it's not 32 by 32. So that's the idea. Okay, so let's take a look at your numbers. We are done with this on